Hi everyone. So, the first week topics we are going to cover the following topics in week 1 like reviews of basic equation of theory of elasticity. Under that head we may cover that how to represent a generalized Hooke's law or the constitutive relations, then the strain displacement relations, differential equations, transformation rules for stresses and strains. In part B, we will do the energy principles. Basically, these energy principles are useful for developing the plate or shell theories. Then we will classify the shell theories based on various approaches, whether it is a thin plate shell theories or the thick plate shell theories. Before going to the main topic, I would like to explain where these theories are helpful or applicable. Like you see the many structural elements like the building of IIT Delhi, that is a triangular shaped roof, or you see that lotus temple in which this shape is on a curved shell shape, and you see that this is also a picture where the tapered element of a shell. Not only in the structures but also in the bridges you see that various truss elements, in aerospace industries, in shipbuilding, cruise and oil tanks. If we can divide that all structures into a small elements, either they will be a beam or a plate or a shell. So, any structure, any machine, any component can be subdivided into 3 basic elements: beam, plate and shell. If we are able to predict the behavior of that basic element with the subjected to different kind of loading, different kind of boundary conditions, definitely we can analyze these structures, because these structures are made up of this. So, applying the continuity conditions or some relevant assumptions, we can analyze these structures. So, very first thing comes that beam, the whom or the qualification of a beam, that in a structure if you find a component whose length is very long compared to its width and thickness, then we can treat as a beam or a bar or a rod. But how much? It cannot be infinity. Theoretically it should be infinity, but in practical application, that how much that minimum should be. So, if we take that width is twice of h, the length should be greater than the 20 times of h. If you find any element, whether it is in a bridge or in a building or in a ship or element, if that qualify this criteria, you can treat as a beam. Further, the classification of a beam, that if a element like this and subjected to a transverse load, then we treat as a beam. If this is my longitudinal axis x and z. But in a case of rod or a bar, if same element is subjected to a axial loading, whether it may be a tensile or it may be compressive, it depends upon the situation, then we treat as a bar or a rod element. If the same element is subjected like this and in vertical direction, compressive loading, then it will be treated as a column element. Similarly, we are coming, because our subject is the theory of plates. So, the definition of a plate, it is a 2-dimensional element. So, its length and width are comparable and thickness is small. Generally we take thickness must be small, it may be higher. So, if you define a plate when A and B are the thickness and width and it is less than 2h, very less than, then we can treat as a plate. Then further, shell or cylindrical shells. Just in the shells, they may be cylindrical, conical, spherical. So, 2-dimensional shell elements, that length and width are comparable and thickness is very small. But how do you differentiate between a plate and a shell? That differentiation is that middle surface of the plate is flat, whereas the middle surface of the shell is curved. So, I am just going to give you example. If you have a curvature, then we will treat as a shell. If it is a flat, then we will treat it as a plate. I have used a term middle surface. Generally, we define a body or a component like that, let us say a middle surface, and at the thickness of h by 2, if we add another plane similarly like this, so this will make the surface, complete plate. So, this surface defines the geometry of the plate. If this is flat, then it will be treated as a plate. If this is having some curvature, then this will be treated as a shell. So, what is the direct application of this course, where we can use or the knowledge which we are gaining through this course we can apply? Next, that what will you be able to do that after completing this course? First, you will be able to develop the governing equations and boundary conditions for the rectangular plates for isotropic materials. Then, in future, you can extend your approach to plates made up of advanced materials. They may be piezoelectric or the recent functionally graded materials. During the course, wherever possible, I would like to expose you that how you can expand the present theory to the advanced material. Then you will be able to model plate and analyze in Abacus or any finite element software, basically in which I will prepare a one short video for you, so that you will learn how to model a plate in Abacus, 3D modeling of a plate or a 2D modeling of a plate, so that in future if you develop your plate theory, you have to compare your results, this will be helpful. Next, you will be exposed how to write your own code, at least for the analytical solutions. Further, it will provide the basis for developing the FEM solutions. It may be the primary requirement for understanding many other related problems, like if you understand a linear analysis of a plate, then you can go for a nonlinear analysis of a plate, buckling of a plate, or a transient analysis of a plate, or doing the control of the plates. So, from here our the basic terminology starts. So, basic index notation and representation of stresses and strains. So, undergraduate levels you may be exposed to this kind of scalars and non-scalar quantities. So, I am just going to give a basic information that we are going to use during this course. So, first is the scalars. So, how do you define a scalar quantity? A scalar quantity is represented by a single real number or the complex numbers. The examples are temperatures, volumes, density, etc. Then the non-scalar quantities, which has magnitude as well as the directions. There you have understood, I think, up to class 12. Even during the undergraduates, we used to do number of analysis using the vector analysis, like in basic course engineering mechanics. So, whole engineering mechanics solution is based on the vectorial approach, in which direction as well as the magnitude taken care. What are the examples? The basic examples are the displacement vectors, force vectors, accelerations and so on. But there are some other quantities like the stress and strain, which require two directions. So, then how do you define? What do you call it? So, we cannot call it vectors. So, we call it second order tensors. Then vector is known as tensor of order 1. So, in that direction, I would like to tell that if you have to define mathematically 3 raised to power 0, it means scalar will have only one quantity. For the case of vector 3 raised to power of 1, it will have 3 components. For example, if you talk about a position vector r, it may be rx of I or whatever Ry of j, Rz of k, or sometimes you write just x, y and z. Similarly, the force Fx of I, Fy of j plus Fz of k. So, you have a 3 quantities. When you are talking about the second order tensor, then it will be 3 raised to power 2, which is equal to 9. So, stresses or strains will have a 9 component. Then epsilon ijk, some permutation kind of things, or sometimes we use this kind of symbols in the compatibility relations. Then the stiffness or compliances Si, or I will write 3 raised to power 3, 27. If we talk about compliance and stiffness, this is 3 raised to power 4, 81 components. So, for a case of vector, if you want to know the state of a displacement, at least you need 3 components to completely define the state of that displacement vector. If you want to know that state of stress at a point in a body, then you need 9 components. For example, if we talk about sigma xx, sigma yy, sigma zz, tau xy, tau yz, tau zx, and 3 are yx and zy and xz. So, in this way we require 9 component of stresses to define a state of stress. Then the some symbols permutation or computations, then they require 27 components, and if we talk about the compliance and then stiffness, they require 81 components. So, basically we define S, I, J, K, L if we talk about in terms of index. So, whenever you find, generally in advanced theory books like theory of plates, you will find that these are written in terms of index. So, if you find a 4 index, it means it is a 4th order tensor and it will have 81 components. So, we can define a stress, second order it means sigma ij. If we talk about vector, it means ui or fi, only 1 index, 2 index, here 3 index, here 4 index. So, you may be aware, so our aim is just to tell you that this kind of things are available. So, we defined it as second order tensor, then third order tensor and fourth order tensor. So, their addition, multiplication or their further transformation follows some different rules. So, how do you define a stress? So, definition of a stress, if this body is subjected to number of forces, let us say P, then if you take over that body small area and the resultant force will say that delta F working over in delta A or delta P equivalent to delta P, no problem. Then at that point, if this area reduces to a point, area tends to be 0, then we will say that stress on that point acts in a normal direction delta P over delta A. So, in a cube, how do you define these 9 component of stresses over the cube? Basically, this part is covered in advanced solid mechanics, in undergraduate courses or sometimes in a postgraduate courses under the head of theory of elasticity. So, if I define, this is my x axis, this is okay, if I will say this is my y axis and this is my z axis, then this face will have a component that this face is a positive face. This will be defined sigma on a x plane. First index tells you the plane position and second index tells you the direction over that plane. If my component is like this, then it will be tau x z along z direction, and the component along this direction, it will be tau x y. So, in this we did define the traction vector or on a plane 3 component of stresses. Similarly, on the top face of this block, there will be sigma zz along x direction, sigma zx, and along y direction sigma zy. Similarly, over this face, it will be sigma yy, then sigma yx and sigma yz. So, we can write all 9 component in the matrix form. So, we write that sigma in a matrix form 3 cross 3. Most of the time we use this kind of notations. So, that is why sometimes we call stresses and strains are the matrix variables. Because we can write. Then the equation of equilibrium. Equation of equilibrium, I think in undergraduate you are aware about that force balance equation. Similarly, you have a moment balance equation. Which is equal to mx of I, my of j, mz of k equal to 0. If we talk about a continuous system and in terms of using the stress kind of thing, so we will write this is basically equation of equilibrium with body force and inertia. These terms are body forces, these terms are inertia terms, where sigma x comma x is nothing but partial derivative of sigma x x with respect to x. So, this is also a standard notation when we use a comma, like if I say sigma x x comma of y, it means sigma x x derivative with respect to y. So, whenever you encounter in theory of elasticity, in theory of plates a comma, by default it does assume that okay, this is the differentiation with respect to that quantity. Otherwise, they will clearly specify that it does not mean the differentiation if it is other than that. So, this is the equation of equilibrium which can be obtained by the various ways. The first is force balance. Sometimes we can find out from the energy principles. So, with the help of force balance, how do you find out? Let us say along only one direction I will explain. So, next 2 directions one can any time rewrite or derive the set of relations. Let us say in this is taking a differential element, if this is my dx, this is my dy, this is my dz. So, if over this face in a negative direction, let us say sigma xx is acting. So, over this face how much? It will be a sigma xx plus del of sigma xx over me x into del x dx over that length. So, using these concepts similarly from this top face along the x direction, that tau zx over this direction, tau yx. So, on the back face also. So, along x direction if you say, and total force working over this area will be sigma xx dy and dz, and here sigma xx, sorry, dy and dz, and sigma xx del x dy and dz. So, if you do some mathematical simplification, the first equation can be obtained. Similarly, the second equation can be obtained and third equation, but in our course we have to just remember these set of equations. We are not going to derive these relations, because this relations, the derivation is given in undergraduate courses where you can derive that how to derive this equation of motion. For our case, we have to just use this set of relations. Now, the concept of the strain. So, basically strain related to the deformations. Ultimately, if we talk about in terms of measuring point of view, that displacement of the points. Let us say in a body there are points, material points. So, after the applying forces, so before deformation, let us say this point is A, this is B, before deformation, and after deformation, let us say this point is A and this becomes B. So, that distance. So, relative change, the strain is related to the deformations. Further, we can define that normal strain which measures the elongation or contractions along x axis, y axis and z axis. Similarly, like your, if we that this index first tells you the plane and second index tells you the direction. Similarly, you have a normal stresses. Sometimes some of the students or persons are not aware, in undergraduate levels just we denote that strain by epsilon and stresses by sigma. So, they are not aware about their components. So, I am thinking that I will just review the basics. Let us say these are the components, epsilon xx, epsilon yy and epsilon zz, and these are known as normal strains. Similarly, the normal stresses will be sigma xx, sigma yy and sigma zz. Then we will call about shear strain. So, in the shear strain, measure of the relative rotation of the two lines. So, if we talk about a plane before deformation, if this is the reason, so after the deformation, how it would look like that? That angle. So, they are denoted by, if we talk about epsilon xy, epsilon yz, epsilon zx, all these are known as shear strains. I think you are also aware that we relate that gamma xy. So, basically this is the twice of epsilon xy. So, we relate that gamma xy is the twice of angle of that epsilon xy, one this, and gamma yz epsilon twice of yz and gamma zx twice of zx. Similarly, you have a shear stresses, concept of shear stresses. What is that? Tau xy, tau yz and tau zx. These are also known as shear stresses. Then the most important part, relations between strain and displacement. Before going to there, I would like to tell you, when we denote small epsilon, this is known as small strain, small deformation or strain gradient. These are all small strain. If we denote by capital Ij, or if I say capital Exx, then it will be large strain. So, strain displacement relations. So, you may be aware that epsilon xx nothing but del u by del x. If u is the displacement along x axis, v is the displacement along y axis, w is the displacement along z axis. So, do not confuse. In undergraduate level sometimes u, v, w are related to velocities in mechanics. So, but here when we talk about strain, these are the displacement. Component. So, this is not, this is the displacement component. If u is along x axis, displacement y x axis, then we can write epsilon x x is nothing but del u by del x, epsilon y y is nothing but del v by del, sorry, this should be y, and epsilon z z should be del w by del z. So, this is called linear normal strain. In journal, we can write epsilon I j equal to half of u I comma j plus u j comma I. This is the normal, or I will say that small strain, linear strain definition in index form. So, this is the definition of linear strain, and these are the corresponding to non-linear strain. That is why I told you, if you are able to develop a set of relations or theories for considering the linear strain, then definitely you can develop, if you consider this part, non-linear part in the strain, then non-linear theory of plates. Now coming to the Hooke's law. So, generally you have gone through that Hooke's law for 1D case, that stress is directly proportional to the strain. If you remove this proportionality constant, it becomes y epsilon, or sometimes we called it E. So, this is known as Young's modulus of elasticity. But what about the 3-dimensional case? If you have plate or a shell in which you applied a stresses in all 3 directions, and then you will have a strains all 3 directions. So, we require the more general definition for this constitutive law. So, general definition can be treated as sigma ij, second order tensor, then stiffness and epsilon kl. So, this is the standard form of writing constitutive relations for 3-dimensional case, that sigma ij, c ij kl, epsilon kl. Or in a matrix form you can write sigma equal to c epsilon. So, I would like to here say that here sigma in generally it is 9 cross 1, and this matrix is 9 cross 9 and 9 cross 9, because we have 9 component of stresses. But as you know that by using the moment balance, so we have proved that sigma tau yx is nothing but tau xy, tau yz is nothing but tau zy, tau zx is nothing but equal to tau xz. So, if we use these relations, then we will say that 6 independent component of stresses. So, in that case it will be sigma, which will be 6 cross 1 C, which will be 6 cross 6 and epsilon 6 cross 1. So, out now you see that if you use this symmetry, then theCijkl reduced to 36 elements. In inverse form, if you want to know what is the strain in terms of stresses, so it will be related by through a matrix S, where S matrix is nothing but this is the inverse of C. So, basically this law is valid for a elastic material, elastic anisotropic, or we can say that 3D in which are non 3-dimensional case. So, basically it is the elastic material. If we talk about the piezoelectric material, what extra things will come up here? So, you see the definition of stress CE same, then extra, this is contribution to the piezo component, this is contribution to the thermal component. Similarly, here due to piezo material behavior, and this is due to thermal. So, suppose I have explained you how to develop plate equation, plate theory using this relations, and if somebody is interested to develop thermomechanical case, in that case he has to take the constitutive relations this and this beta. If further is want to develop for a piezo case, then they have to consider this extra term. This is okay up to here. As soon as this terms comes into the picture, so their corresponding new relations also comes into the picture, that electric displacement in terms of stresses, in terms of piezoelectric constant, in terms of thermal. So, when we are interested to develop set of solutions for a, let us say, piezoelectric material, you have to take care mechanical, constitutive relations and electrical also. So, these are the two, or if we talk about this system, two new set of equations will come into the picture. If we talk about kind of piezo-magnetic, in which mechanical, piezoelectric, magnetic and thermal, then the relation will look like this. You see that this is due to M for mechanical, E for electrical, MS for magnetic. So, this constitutive relations further extended. So, sometimes students get afraid, oh, I have to do for functionally graded or shape memory alloys or some advanced material. So, you have to just find out those set of relations. As in mechanical engineers, we have to just get these relations, that what is the constitutive relations available for this kind of material. If this relation is valid, definitely we can analyze, we can do the stress analysis or vibration analysis or any transient analysis. Similarly, now you have added a magnetic. So, this is due to electrical component and this is due to magnetic equation. I think now you have get the idea that the basic relations is extended from elastic to piezo, piezo to magnetic. In later on maybe some a material may exist, this may have some other kind of property, optics or some other. So, maybe some optical parameters may be added. And the relevance, whatever we are doing in the course or why we are studying these theories? Are they really useful to the current area of research? Whether people are working in a current area of research, I will say yes. So, you see that these days, you see that free stress as is in smart piezo composite structures, basically it is a plate. They have done its control analysis using a, so the relevance whatever we are studying in this course, whether this material is relevant to current area of research, I will say yes. These days the using the advanced materials like piezoelectric, so they have done the free stress analysis for a smart composite piezoelectric composite structures. So, using a different approach. So, you see this current paper. Then the next they have done the very recent that free vibration analysis of 3-dimensional multilayered magneto-electroelastic plate, whatever I have relation given here. So, these are valid for different boundary conditions, clamped or free boundary conditions. Then you see that for the Levy type functionally graded plate, this is the plate which is having a boundary conditions 2 edges simply supported, other edges 2, but the material is different. So, we have to develop a altogether new approach to analyze that plate. So, these whatever we are teaching, going to teach in this course, that is having application in the recent research, if different kind of material or different kind of boundary or maybe different kind of shape. Sometimes these days we are just able to analyze a rectangular plate. The plate may be of a hexagonal shape or plate may be of a triangular. Then you have to think their solution. Even that solution of arbitrary any shape plate is, I would like to say that analytical solutions are not available. We have only up to that numerical solutions for arbitrary supported plates. Sometimes we are having a just very basic solutions for the case of triangular plate or some this kind of plate or some, I will say that skew plate, but the detailed analysis or detailed behavior using some analytical technique or using or the more accurate still is required. So, we are talking about that compliances CIJKL. So, there I told you they have a 81 component, but if you use the symmetry sigma ij equal to sigma ji, then this reduces to 36 components. Further, if you use that symmetry Cij is equal to Cji or some Ckl equal to Clk, something like that, whatever. So, basically that reduces to further 21 independent elastic constant. So, if you have a material which is having no plane of symmetry, then you have to give 21 constant to find out the stresses relations with the strain. If you want to know the stresses and you have obtained some strain, then you need here 21 constant, then only you can obtain the stress or the strain behavior. Then there are materials in which we have a one plane of symmetry, then it reduces to 13, and if we have a two plane of symmetry, then it is further reduces to 9. Being a mechanical engineer or I think in this zone more physics or chemistry kind of things or even that some relevant material also there, but we talk about composites or sandwich plates, they are generally treated as a orthotropic materials, or if we talk about a piezoelectric materials. Then the another is transverse isotropic material. So, most of the time you will find in the literature that people have studied using the transverse isotropic material, in which you have only 5 independent elastic constant. And the last, the most famous and or most ancient material is a isotropic material, in which have a 3 plane symmetry, in which only 2 independent elastic constant. What are they? E and nu. where G can be find it out like this. So, G is not an independent constant. So, whenever a isotropic plate is analyzed, so solutions is written in terms of E and nu. But if you talk about transverse isotropic material, orthotropic material, then we write the solution in terms of C or in S complete components C11, C12 like this. So, compliances S11, S22 can be related to the engineering constants, basically E1, E2, E3, Young's modulus, or sometimes we call it Y1, Y2, Y3. So, if you know that engineering constants, because students are generally aware about the Young modulus, not about these compliances. So, we can obtain these compliances if we take 1 over Y1, 1 over Y2, 1 over Y3. Similarly, if we know the shear modulus, we can obtain the compliance S44, S55, S66, S12, S13, S23 can be obtained using the Poisson's ratio. So, I think some of you may be first time encountering this kind of notations that mu21, mu31, mu32, or you may be aware about that, but for the case of orthotropic materials, so mu12 is a independent constant, mu23 independent constant, mu13 these are the independent constant like E1, E2, E3, then G23, G31, G12, so 9 independent constants. So, if you know E1, E2, you can obtain S1, S2, S44, S55, S6 and so on. Further, if you want to transfer, suppose you know a material is made of this composites or some fiber and the geometry, let us say this is your x and y aligned like this, but you have aligned that material axis at some angle with respect to this. Or very suitable example is that let us say a composite lamina. Here fibers are aligned like this, okay, parallel to the sheet x axis. There is no angle, but if fibers are at an angle, some angle, then we have to obtain the effective or I will say the transformed elastic constant along x direction Ex, along y direction. Material is oriented in this direction, so this direction is 1, corresponding perpendicular direction will be 2. So, one can obtain how to find out this transformed one. So, these transformation rules are given in very basic book. I would like to say that Martin Sath or in some Bhaskar book also, that J. N. Reddy, Theory of Plates. So, their transformation is clearly explained, how to transform a first order tensor, how to transform a second order tensor, how to transform a third order tensor. But for our present scenario point of view, I would like to say that first order tensor, if we define by AI, let us say UI or Fi, so then Qij is known as transformation matrix. It will contain basically cosine angles. Similarly, the second order tensor double index in the, then it will be 2 transformation matrix and that basic elements. So, Qij basically components inside that matrix Q11 is nothing but cos of x1 dash comma x1. What is that? If let us say x1, x2, x3, these are our three basic axes, and material axis is rotated to x1 dash and x2 dash and x3 is matching to this. So, basically the angle between this x1 dash to x1, then x1 dash to x2, x1 dash to x3. So, q11, q12 will be, here it will be j basically I and x2. So, in this way we can obtain the components. So, details are given in J. N. Reddy book, Theory of Plates, or Martin Sath book. One can go, and very basic example are also given. They have given like a component 3, 2, 1, some a, and this angle is given, let us say 30. Then what will be the ai dash? So, just you have to obtain x1 dash to x1, x1 dash to x2, x1 dash to x3, and then x2 dash to x1, x2 dash to x2, x2 dash to. So, similarly you can obtain those cosine components and multiply with that. That will give you the transformed vector, transformed second order tensor, if you talk about the stresses or strains. So, in matrix form it can be written like this. Let us say B, which is a matrix, it may be stress, it may be strain, 3 by 3 components. So, Q, B, Q transpose. If we talk about a vector 3 cross 1, it will be 3 cross 3 and 3 cross 1. Then you are talking about compliances Sij(k)L, which is a 4th order tensor. So, you can transform like this. I am just exposing you that these are the relations are available, you need not to remember, only you must be aware that this can be transformed and this kind of relations are available. These relations are available in the basic theory of elasticity books. So, we are not going to remember these relations, we are just going to use these relations later on wherever we required. So, just I am giving you that basic informations that this you required for developing the plate theories.